All right, today we're going to talk about the different types of correlations that we observe. Oh, sorry, let me change my screen share. I know it's exciting for you to watch me fumble around with the computer. All right, so we're going to talk about the different types of correlations we encounter in this course. The first one and the biggest one, the most important one, is Pearson's correlation coefficient, named after Carl Pearson. You know he must be important. He has his portrait painted. This statistic addresses the relationship between two interval ratio variables. Pretty much nobody ever says Pearson's correlation coefficient anymore. They just refer to it as R. It's got its own symbol, which suggests pretty important value. We can also use this in addition to using it for two interval ratio variables. We can also use it for dichotomous variables, or variables with two categories. That's a special case of this. There's also other techniques for doing that. Carl Pearson is certainly among the biggest names in the history of statistics. Without Pearson, we would simply not have modern statistics. He discovered many of the statistics that are in common use today, and we could say that the basis of most modern, or at least modern frequentist statistics, it stems from his work and the work of a couple of others. Pearson was interested primarily in the study of heredity and genetics, and like many people, many old white people back in the day, he was interested in the study of heredity and genetics because he was a big old racist. He had views on what's called eugenics that everybody would agree are just horrible. Views such as, focused on selective breeding, and whenever we talk about selective breeding, that's just a way to say, let's make more white people. So please do try to separate Carl Pearson, the man, terrible human being, from Carl Pearson, the statistician, who made giant contributions. The contributions themselves are mathematical. They have no shred of his beliefs in them. But I'm always uncomfortable discussing Pearson without discussing what a horrible human being he was. All right, Spearman's rank order correlation. This is Spearman. Spearman was interested in the relationships between ordinal variables, or you could use it for a single ordinal variable and an interval ratio variable. Spearman's work focused on hierarchies of intelligence categories. A lot of work in statistics and measurement come out of the intelligence literature. So he's interested in developing these categories. He's got a hierarchy of categories. He's dealing with ordinal variables, which is why he needed to adapt Pearson's work to those sorts of variables. And from everything I've read about Spearman, there is no evidence that he is a racist. So yay, good for Spearman for not being an awful racist. All right, point biserial correlation. This is a statistic that isn't named after somebody. It's just a statistical procedure called point biserial. It's the correlation between a dichotomous variable and an interval ratio variable. This really isn't very useful, as we can use Pearson's for this, but I wanted to mention it because I know people Google stuff and you might come across this. It's a very special case statistic. It was really just developed for a shortcut calculation approach. Dichotomous, that just means having two categories like yes or no questions. And more commonly, we do some other procedures for these types of data, like the Pearsons. All right, how do we interpret correlations? Correlations range from -1 to +1, so that's something to keep in mind when we're calculating correlations, is that if you're getting something outside of that range, it's wrong. Closer to 0 means smaller, so closer to 1 or -1 are the larger relationships here. The positive and the negative values here don't imply any less or more of something. They just get a direction of our relationships. You'll see on the internet, again, if you Google things, you'll see rough guides to correlations, saying about 0.1 is small, 0.3 is moderate, 0.5 is large. You'll see these guides for a lot of things in statistics, and I would say that pretty much any time you see a shortcut or a rule of thumb type piece, it's almost always wrong. So I would ignore this guide. Usually during class, people start to scribble this down because they think it's important, and then I have to tell them to tear that page out of their notebooks. All right, why isn't this guide useful? Well, it leaves out context. If we don't understand the context of the relationship, then we have no business making judgments about what's small or moderate or large. So here's an example of context. In the United Kingdom years back, there was a large-scale study of aspirin therapy and reduction in heart attacks. It was a double-blind study, which meant that people didn't know what pills they were taking, and the people giving the pills to them didn't know what pills they were taking. This study had to be terminated prematurely because it was so clear that aspirin was an effective treatment for heart attacks. You have older people, many of them do take an aspirin every day. The results were so striking that it would have been unethical to continue to give half of the participants the placebo or the fake drug. So it must be pretty strong, right? So you're probably thinking now, wow, that correlation must be big. More aspirin versus reduction of heart attacks must be a giant correlation. Actually, the size of this correlation that was deemed so valuable was negative 0.03 between aspirin use and a reduction of heart attacks. That may seem really tiny based on that scale that we saw, but practically this means it's something like 2 or 3 people out of every 100 are in the aspirin group, 2 or 3 fewer heart attacks out of every 100 people. And when you think about that in practical terms, that's kind of a massive effect. That's an effect that has considerable importance. When you think about it even further, when you think about the cost of this treatment, aspirin costs what? It's about a penny a pill. You could get a year's supply for about $4 at Costco. Even if you buy the fanciest aspirin there is, you probably would be hard pressed to spend more than $10 or $20 a year for the medicine. So very, very low cost, saving 2 or 3 people from out of every 100 from heart attacks. That is a really effective treatment. But let's turn that context around. Let's say that this was the result for a drug that cost $50 a dose, and you had to take it every day, and that would cost about $18,000 a year. Would it be worth it then? Well, maybe not. Maybe not at that point. But what if this was some sort of treatment that people could implement at home, such as walking 30 minutes a day? What does walking 30 minutes a day cost? It costs nothing. Even if it has a minimal effect, you want to recommend it because it has some effect. All right, here is the relationship between self-esteem and happiness, something that we'll look at and calculate by hand. I just wanted to show you what the scores that we're going to work with look like. You can see we've got scores on self-esteem scale, scores on a happiness scale. We've got some output from R. We'll talk about how to run this in R in a little bit. And you can see we get a correlation of 0.48. What does that tell us? Well, 0.48 tells us that people with higher self-esteem tend to be happier. I'll show you how we get to that in the next set of slides. So we'll do some calculations based on this. And if you look at a graph here, once we put a line in here, you can see that people with higher self-esteem tend to have higher happiness scores. That doesn't mean it's the same for everybody. We've got somebody over here with moderate self-esteem, but very low happiness. So it's not going to apply to everybody, but the general pattern is that positive relationship.